Hey, and welcome to the second part of 8.3. Today we're going to be looking over the application of the unit circle. So you should have already watched the video about how we create the unit circle and what it actually means. So today we're going to be putting that to good use. So let's go ahead and let's get started. So here we go. Okay, so today you'll notice that I have printed off a blank unit circle. You can draw these. I just wanted to make sure that I had extra room and that you'd be able to read it. So let's start off. We're using radians in the unit circle. So we've got radians in the unit circle. Now, radians is a new form of measurement that several of you have started asking about, because when you start plugging in things like sine, cosine, and tangent, you're getting back values that aren't what you're seeing in my videos. And that's because you're probably using degrees and not radians. And let's take a second to explain what those are. A degree is a unit of measurement from the central location. And so what that means is that when we look at a degree, we're looking at how many angles we're changing. What's the change in the internal part of the circle? That's different than what we're about to work with today. Today we're going to be working with a radian as well. And a radian is a unit of measurement from the outer, I think there's two T's in outer, location. Basically, we're looking at the circumference. And so with a radian, what we're doing is we're measuring that same change, but instead of right here in the center, we're saying, okay, what's the difference right here? And that's where we're measuring. It's not central, it's on the outer edge of the measurement. So let's go ahead and let's take a look at the conversion rate between the two. So a degree, from what we know presently, let me actually move this out of the way, so that way it's just blank. A degree is 360 degrees, and that's how we show it. 360 with a little circle up at the top. Most of you know how to do that. With radians, is 2 pi. And what we do is we say radians. Now, if it just says 2 pi and we don't actually have rad, we're assuming they're radians. From this point forward, most mathematicians use radians. Very few actually use degrees. If they do use degrees, they'll signify, hey, this is a degree. But if you get a number like 2, it's assumed to be a radian, because from this point forward, radians are the preferred unit of measurement. So if you ever need to convert something, you use this relationship and you set up a proportion. So let's say to convert, so with conversions, I know I set up 360 degrees is equal to 2 pi radians. And I'm not even going to put the radians because, like I said, we're assuming this is true. And whatever value you have, let's say you have X degrees, we're going to go over to find Y radians. And you plug in the one that you have and you solve for the one that you don't. So if you're switching from radians to degrees, plug in this number and you solve for X. If you have degrees and you switch over to radians, we plug in X and we solve for Y. And we're about to do some of these here in just a moment. Box that up. So we know that we're going to be referencing that quite a bit. So as of right now, let's take a look at what that means for this thing right here. We're going to be converting the unit circle. So our first step is we are going to convert. So we can, actually, we're not even going to convert the first step. The first step, we can do degrees, and we know how to measure the degrees. So with a unit circle, we know that this is going to be 0 degrees or 360 degrees. Depending on if I start here, it's at 0, or if I've gone all the way around, it's 360, because this is our what we call starting angle. In fact, I probably should have written that above and below, but that's okay. Normally the way I write it is I write a 0 above and 360 below, so I know which angle I'm hitting at. And then as we creep around, if we remember, we had our 30, 60, 90 triangle was the first one. So I know this is 30 degrees. I know halfway around this quadrant is 45 degrees. And then this is my 60 degree location all the way up until I hit 90 degrees. And we should remember that we created triangles yesterday giving those markings. And so now we're just going to keep counting. So if this is 30, 60, 90, add another 30, I get 120. Add another 30, I get 150. 180. And that makes sense because that's 180 degrees, right? That's half of 360. Now if I keep going around, I get 210, 240, 270, 300, and 330. And all the way up to 360. So I went up by 30 each time. Now we also notice that we have this 45. So 45 once, 45 twice, 45 3 times makes 135. 4 times, 5 times would be 225. 6 and 7 would be 315. Jokingly, the way I remember these is way back when I used to be a really big gym goer, I knew that these were the 45 plates. So you should recognize these if you're repping out nice sets with just 45 plates on the side. However, if you don't go to the gym, that analogy is completely lost onto you. So what we're going to be doing is we're going to be switching all of these into radians, because like I said, the unit circle typically is measured in radians and not necessarily degrees. We found the coordinates yesterday, so today all we're doing is we're finding what are these angles. And this should be really easy. With 0 degrees, we know there's 0 radians. So I'm going to do this in purple. So 0 radians. I also know that if I go one full circle, what's the circumference of a circle with a radius of 1? Well, I know the circumference is, I think it's 2 pi r. And if my r is 1, it's just 2 pi. And that's where that 2 pi comes from. It's the distance around the circle. Well, if that's 2 pi, what is half of that? Pi. And what is half of pi for this middle piece? That's pi over 2. So I'm going by half pies. 0, half a pi, 2 halves of a pi, which is a whole pi, 3 halves of a pi. So 3 halves of a pi. We've got our first 4. And now comes the other part. Now we have to count by these values. So let's take a look. If I have pi over 2, what is half of a half? A fourth. So I know half of my half is going to be pi over 4. And I'm going to count by pi over 4s for all of these 45-degree angles. So that's 1, that's 2, this would be 3 pi over 4, 4, 5 pi over 4, 6, 7 pi over 4, and 8 pi over 4. And 8 over 4 does reduce down to 2. So now we have our 45s set up. And then lastly, we got to figure out this. So I'm taking this half and I'm dividing it into 1, 2, 3 pieces. So what is a third of a half? Well, a third of a half is a sixth. So this is pi over 6, which means this is 2 pi over 6. And doesn't 2 over 6 reduce down to 1 over 3? So pi over 3. So 1, 2, 3, 4 pi over 6. Doesn't 4 over 6 reduce? Yep. 4 pi over 6. 5 pi over 6. That doesn't reduce. 6 pi over 6 is 1. 7 pi over 6. 8 pi over 6. And so I know 8 over 6 does reduce down to 4/3. What were we at? 8 pi over 6. 9. 10 pi over 6. 10 reduces down. And 11 pi over 6. Oh. And so we have these values. And so now that we've converted the entire unit circle into radians, just by doing some basic, hey, I've split these up. What we can do now is we can now solve for a few radians. So the first thing I want you to do is we're going to be converting some degrees into radians and some radians into degrees, and we're going to be flipping back and forth. So we have that copy down. Now let's hit up a few problems. So my examples to start are going to be, I need to convert 210 degrees. That's number 1. Let's say my conversion examples. I need to convert, number 2 is going to be negative 160 degrees. It's a negative degree marker. Zoom in. I'm going to convert 3 pi over 2, and I'm going to convert negative 13 pi over 15. That's what I'm going to work with. And so let's take a look at how we're actually going to solve that. So with converting degrees to radians, I'm going to consult this over here. I have degrees, so I'm going to fill in this. Some degree over a circle is equal to some other radian over a full radian. So I know that, do this in black. I know I have 210 out of a full circle, and that's some number out of 2 pi. I just need to figure out what x is equal to. So I should have given a little bit more space here, but oh well. So as of right now, I'm going to cross multiply. I'm going to say 210 times 2 pi, and I get, what is that, 420 pi. X times 360 is 360x. And then I divide this by 360. X equals 420 over 360. I notice that I can reduce these both by 10. 42 over 36. Both of these are divisible by 6. That's 7, and that is 6. 7 pi over 6. So I know I'm going to move that over there. So I know the fact that this is 7 pi over 6 radians. And because I did the conversion from degrees to radians, I am going to necessitate that I label that. So let's do it again. So with negative 160, I know I have negative 160 out of a full circle is equivalent to some unknown number out of a full circle over here. And I'm just going to do the same thing and cross multiply. X times 360 is 360x. Negative 160 is going to be negative 320 pi. Is that right? Yeah. And then to solve for x, I just divide both sides by 360. Cancels those out. So x is equal to whatever this reduces down to. Negative 320 over 360. The zeros cancel out. 32 and 36, they're both divisible by 4. which is going to give me 8 over 9. Boom. So we get that. Okay. Now let's go the other way. Instead of converting degrees to radians, let's fill in this side and not know how many degrees it is. So let's solve 3 pi over 2. And again, we're going to move this over to give us some more room. So in this case, I know how much I have out of 2 pi. And that's equivalent to some unknown number out of 360 degrees. Okay. And I'm going to cross multiply. So over here on the left, I have 2 pi x. On the right, I have 3 pi over 2 times 360. And so I can look that as whatever 180, because that can reduce down in half, 180 times 3. And 180 times 3, if I plug that into the calculator, I will get 540. 2 pi x equals 540 pi. Divide both sides by 2 pi. 540 divided by 2 is going to land me 270. And my pi's cancel out, so 270 degrees. Do we see how that works? We just set up a proportion, cross multiply, and solve for what we don't know. Let's do one more. So negative 13 pi over 15, I know this is some radian value, so I put a full radian circle is equal to a full degree circle. And I don't know this value. So I just cross multiply. 2 pi x equals negative 13 pi times 360 all over 15. And so I can do this a couple ways. What I'm going to notice is that my 2 pi, when I go ahead and divide that, I'm going to leave this right now. Actually, no, because I can divide 360 by 15. So if I get 360 and I divide it by 15, I get 24. So negative 13 pi times 24 is equal to 2 pi x. If I multiply 13 times 24, I get 312. So 2 pi x is negative 312 pi. The last step is I'm going to divide by 2 pi. Cancels out. The pi's cancel out. And 312 divided by 2. And we get x equals negative 156 degrees. And so this is the longer way of doing things. Could you do that to make the unit circle? Yes, you could. And you could plug in all of these values in and do a proportion every single way. I like to look at it visually and say, okay, half of 2 pi is pi, half of that is half of pi, half of that is pi over 4, and then count by 4s. And then I take that and I divide it by 3, so I get pi over 6, and count by pi over 6s, and then I'm done. I don't need to do, let's see, how many times would you have to do that? 1, 2, 3, 4, 5, 6, 7. You'd have to do this 16 times if you wanted to actually convert this. Otherwise, look at it visually, see what you're going for here. And so step 1 is how to convert degrees into radians. Now all that is to set up the unit circle right here so that we can answer questions like this. So I want you to value or evaluate. I actually have a word for that. Evaluate these expressions. So I need the sine of 120 degrees. 2, 3, 4, 5, 6. I need the cosine of pi over 2. I need the cosine of 135. I need the sine of 11 pi, that's an 11 if you believe me, over 6. I need the cosine of negative 315. I need the cosine of 3 pi. And so we're going to work on these 6 expressions, and we're going to see how exactly they work. And so I'm going to leave this over here just so. I can extend this a little further so we can get some more viewing. Nope, I can't. It doesn't let me. Okay, so we're going to be using this circle over here to evaluate these things. Now, yesterday we talked about sine, and the first thing we're going to need is I'm going to need SOHCAHTOA. So sine is opposite over hypotenuse. And if we think about that with the unit circle, what we're looking at is with the unit circle, we create a bunch of triangles, no matter how it's oriented. But I know that in that central angle, sine is opposite. That's the distance up. So we talked about the distance up on these is basically just our y value. The hypotenuse is always going to be our radius, which we know for a unit circle, our radius is always equal to 1. And then the adjacent angle, well, the adjacent angle is this angle right here, which is going to be your x value. So let's keep that in mind as we look at this. So when I look at the sine of 120 degrees, that's opposite over hypotenuse, y over r. So I need the y value over the radius. 120 degrees is right here. That is going to be a 60-degree jump, because from 180 to 120, that's 60 degrees. So what I'm looking at is I'm looking at a triangle that is a 60. Zoom in a little bit. So I have a 60, 30, 90 triangle. Hey, we did a bunch of those yesterday. It's going to be my 1, 2, square root of 3. If I'm looking at my y value, it's a square root of 3 over 1, or just a square root of 3. And that's it. Awesome. What would happen if we had cosine? Well, cosine, my 2 in this case, if I look at it, is going to be going to the left. So that is actually a negative 2. So I can separate that from the rest of the work. Okay. So the next thing we're going to look at is, what about cosine of pi over 2? Pi over 2 is right here. Well, cosine, if we look up here, adjacent over hypotenuse, that's x over r. X over r of a vertical line. Well, what is the x value at this point in the circle? 0, right? So there's my sketch of what that looks like. It's going to be 0 over, I have a radius of 1, which is 0. So the cosine of pi over 2 is going to be 0 over 1. I look at the cosine of 135. That's this angle right here. Ooh, that's my halfway point. So I know that I'm going to be dealing with a triangle. In this case, is a 45, 45, 90 triangle. And we converted that yesterday to 1 over the square root of 2, 1 over the square root of 2. Actually, and I'm going to go back and say that's 1/2 over 2. A little bit of typo there. It's supposed to be a 1 to square root of 3. We reduce the radius down to a 1. Forgot to catch that, so edit. So when I look at this, I say, okay, cosine adjacent over hypotenuse, x over r again. So x over r. So I'm looking at my x in this case, which is, because it's going to the left, it's negative 1 over the square root of 2 over my radius, which is 1. So I'm literally just looking at 1 over the square root of 2. I can't have a radical in the bottom, so what I'm going to do is I'm going to multiply both of those. That turns into a 2. That turns into a square root of 2. And there's my answer. Okay. Next up, sine of 11 pi over 6. So this is why we recreated this table. I'm just looking for an 11 pi over 6. Right here. That's 30 degrees down, because from 360 to 330, 30 degrees. So I'm looking at a triangle that has a 30-degree marker right there, which means that must be 60. And so I'm looking at this triangle again. Opposite the 30 is the 1/2, except for this case, because it's going down, it's negative 1/2. This is positive. So square root of 3 over 2. My radius is still a 1. I don't know if you can see that. I think I better zoom in. So what we're seeing right here is my 11 pi over 6 is a 30, 60, 90 triangle that's going down. Sorry, low battery. So sine, if we remember, beginning is opposite over hypotenuse, which, if we look at that, opposite over hypotenuse is y over r. So that's negative 1/2 over 1, which is just negative 1/2. Awesome. Cosine of 315. Well, if I look over at cosine 315, that is my 45-degree triangle facing downward. So I know this is 1 over the square root of 2, 1 over the square root of 2, 1, except for this one is a negative because it's going down again. Ooh, careful here. What did we not account for right here? Negative sign. I just basically did positive 315. We're going the other direction. So if I'm at the 45 down, I'm now at the 45 going up. So it's the same triangle, but a different orientation. So 1 over the square root of 2, 1 over the square root of 2, and 1. Cosine is adjacent over hypotenuse, which is x over r, which is 1 over the square root of 2 over 1. I can ignore that. And to rationalize that, I give them both a square root of 2. Square root of 2 over 2. And I'm done. Last one. We're looking at 3 pi. So if I look over my unit circle, I have 1 pi, 2 pi, 3 pi. So I'm at this line right here. So if I have a line that goes out, cosine being adjacent over hypotenuse, which is x over r, I'm going out to the left. My x is at -1, my r is at 1, so that is just a -1. So I can convert these into actual evaluations. And so the last thing that we're going to do today is a really quick thing. We're going to evaluate when sine is going to be positive and when sine is going to be negative. Let's take a look. So all we're basically asking is, when are they each positive? When are they each negative? Well, if we think about that, again, in terms of a triangle, from that central angle, and I know the opposite, the adjacent, and the hypotenuse. Sine is going to be opposite over hypotenuse because of so, ka, ta, opposite over hypotenuse, or opposite over hypotenuse, y over r. When is the y positive? Well, in quadrant 1, my y is positive, and in quadrant 2, my y is positive. So I have sine of theta and sine of theta. So quadrant 1 and 2. When's it negative? Well, 3 and 4. Okay. When is cosine positive? Cosine is adjacent over hypotenuse, which means x over r. Adjacent over hypotenuse, or x over r, is what I'm looking at. When is my x? I know our radius is always going to be positive. When is my x positive? Which quadrants? 1, not 2 because it's negative over here, and not 3 because it's also negative over here, but it is positive in quadrant 4. So 1 and 4. Which means 2 and 3, it must be negative. So for 2 and 3, my x's are negative. Tangent. When is tangent positive? Well, tangent is opposite over adjacent, which means y over x. Opposite over adjacent, or y over x. And so when is something divided by something positive? I know positive divided by a positive is positive, and a negative divided by a negative is positive. So when x and y both have the same sign. So I can look over here and say, okay, when do x and y have the same sign? Quadrant 1, I have an xy, which make positive. Negative x and positive y. No. Negative x, negative y. Yes, a negative divided by negative is positive. Positive x, negative y. No. So my tangent is in 1 and 3. Which means it must be negative in 2 and 4. And so that is the last thing that we're going to be looking at, is when can we check our work. And so that's it for your 8-3. Remember, we did 2 things today. First off, we converted radians to degrees and degrees into radians because we're going to be, from this point forward, measuring in something called a radian. Check your calculator under the mode. You'll see a lot of them have a degree or radian mode. I think some of them even have a third option. I'm not really sure of that, but always check to make sure you're plugging in the proper unit of measurement. The second thing we did was we figured out what sine and cosine values were for each of the differing degrees and radian measures. And we use our special triangles to figure out where the coordinates are so we can figure out those values. If you have any further questions, make sure to let me know. Take care.